Good morning, Algebra 2 fans. All right, this is the second part of Chapter 8, Section 6, and the problems are called mixture problems, work problems, distance problems. Now, with these, the best way to go through them is through some examples. I'm going to go through some examples right now. Later, I will post another video with some more examples just to give you a little extra help, if you will, in terms of working through these things. So let's start. I'll start with a mixture problem here for you. And how many liters of a 20% chicken broth concentrate would be added to 40 liters? That's how much we have. And it's 50% chicken broth mix to make the final outcome 30%. Now, a smart aleck and somebody will say, well, I'll just do this, I'll do that. There are definitely applications here. Can I guarantee that you will use them? No. But if you're mixing chemicals, for instance, you really don't want to have the bad chemical reaction by mixing the wrong things together or having the result being something more concentrated than what you really want. So what we have to do is kind of set up a chart. And that's the best way I find people have success with these, is doing a little bit of a chart. So in our chart, we want a couple things here. We need the original. We need what's being added to it. We're setting up the problem into a chart from all the words. And then the new result. Okay. So we're talking chicken broth. We'll call it CB. And that's what we're starting off with. And then our totals. So let's look at our totals. Okay, we'll go back into the problem and see what we have. Because we want our final outcome to be something, and we have chicken broth, we have our total. So total, how much are we dealing with here? Well, we're dealing with 40 liters of something. All right. Of that, how much of this is chicken broth? So in other words, in our original, how many liters of this 40 are just pure chicken broth? Well, 50% of it is. So we'll take 0.5 times this. So in other words, half of this, half of it's water, half of it's chicken broth. I know you can do that in your head. Awesome. But remember, we're setting these up for future examples as well. Okay? So we added something to this, right? Yeah, a 20% broth, but we don't know how many liters of it. So something was added to this, X amount. We had 40 liters, we added X amount of this, trying to do what? Dilute this down to here. Now somebody will just say, well, I'll just throw water in there. Well, if you throw too much water in there, then you get off your 30%. Okay? So this was our original amount of chicken broth. Pure chicken broth. Maybe I should put that in there. We added some to that too, right? Well, how much chicken broth was added to the chicken broth? 20% of whatever we're pouring in there. So 0.2 X. So again, look what's going on before you sit there and say, oh, I'm confused, I can't do this and stuff. Stop. We had a total of 40 liters of something. We added something to it. Happened to be that. So 40 liters got some more added to it. We don't know how much yet. Now the breakdown of our 40 liters. Of that 40 liters, 20% of it was 50% of it was pure chicken broth. We added a mixture to it, and 20% of that, if you boiled off all the water, would be pure chicken broth. So we've got our total, and then what the thing is, the chicken broth that's in there. Hopefully that helps you a little bit. So what's that result in? Well, we can do the math. I'm going to write it out though. That amount, yeah, I'm giving the answer away. plus that much in our mixture was that equal to 40 plus x. There's our total. Okay, and then what am I doing? I'm just organizing my data right now. Just organizing my data. Now, what do we want? Well, the problem says right here. We need a mixture that's only 30% chicken broth. Okay, so we need, if let's say we had 100 liters of it, we need 30% of it to be pure chicken broth. So that's what we want over, well, I just did the definition of a percent here. So we're going to set up what we want. Let me put this over here. We want 30%, so we want 30 out of 100 equal to what we want over total. So as we look back to here, it's kind of set up for us already. So when we set our problem up, now I'm going to take that and make it to 20. 20 plus 0.2x. That's chicken broth. That's what we want. So chicken broth to total. Chicken broth to total. Some of you will probably put x plus 40 there. That's not really a big deal. So there's percent chicken broth over total mixture. There's percent chicken broth we want, total mixture. Okay, so let's get to work there. It's a proportion. How do you solve proportion? Right, you're going to cross multiply. Now some of you might do this because those can reduce. Good. So as we do our cross products, you're going to get 200 plus 10 times that, 2x, nice, equals 120 plus 3x. All right, now we start solving. You can do it a couple different ways. I'm going to subtract 120 from both sides. It gives me 80x. I'm going to subtract x, sorry. And subtract 2x from both sides. Equal that, 80. So what's that mean? That means in order to get to this 20% mixture that we want, you need 80 liters of the 20% needs to be added. $80 liters of that 20% solution needs to be added to the 50% to knock it down so it's only a 30% concentration. Okay. One type example. Again, I'm going to have more, so please don't fret. And make sure you're asking, whether it be through email or live sessions. Okay, so let's look at this one. So this one's called a work problem. And why? Because work is being done. All right, so you got Clay. He can clean a large tank at the aquarium in about 6 hours. You can apply this to any type of job that somebody does. When Clay and Matt work together, so now I got 2 people working on it, they get it done in not half the time, but they get it done in 3.5 hours. So it's not the, if 2 people do it, we'll cut it in half. That's not always how things work. About how long would it take Matt to clean the tank if he works by himself? So Clay, 6 hours on his own. Clay and Matt together, 3.5 hours. So what's the work rate, in other words, of Matt? So here's how we want to set this up. And again, the key there is what I said is a rate. So with Clay, he works at a rate of 1/6 of an hour. So in 1 hour, he has 1/6 of the job done. Look at it that way, maybe. So 1/6 of the job is completed, or of the tank. So that's his rate of working. What's Matt's rate? Well, we don't know. So Matt works that rate, unknown. It's kind of what we're trying to figure out. And X is going to stand for, hours cleaning by himself. Now, together, they can get one job completed. Hang on 1 second, I gotta pause. Okay, I'm back. So what's going on? You get Clay, and we'll use his rate. Plus Matt's rate is going to equal what? What they can complete one job, excuse me, one job or one job rate. So if I go back to the total job, they did it in 3.5 hours. So together, their rate, I'll put over here, is what? Together they can get one part of the job done in our situation. So I'm staying consistent. The whole purpose of me doing this, I'm going to stay consistent and make it all rates. So the rate together, one part of the job in 3.5. Clay's rate, one part of the job in 6 hours. It's 1/6 of it done in the mixture. So as we set this up, here's what we have. We have 1/6 plus 1 over x equals our job rate, 1 over 3.5. Again, our job rate, all being rates. So I'm setting up the same way. So now what's this become? Find your LCM. Well, it's going to be 6 times x times 3.5. So look what happens. And some of you are going to see some little shortcuts here, and that's fine. Run with them then. So I'm going to take this 6x and 3.5 times this, and times this. So I'm going to start a shortcut here. I know the 6's are going to cancel out. So what's that leave me? 3.5x. Then I go to this one. I know the x's are going to cancel out. So that means 3.5 times 6. So plus 21. And then I got to take my LCM times this over here. What's going to cancel out the 3.5s, leaving us with 6x. Let's solve for x. So 21, subtracting 3.5 from both sides. Dividing by 2.5, x is equal to 8.4. So what's that mean? It'll take Matt It takes Matt 8.4 hours to do the job by himself. It takes him 8.4 hours to do the job alone or by himself. So Clay, 6 hours. Matt, 8.4. They work together to get her done in 3.5 hours. All right. Let's look at one more type before I end these notes. And again, I'm going to put some more examples out there. It's just going to give me a little bit of time so I'm not making a real long video here. So let's talk about a distance problem. One type. There'll be other types that we talk about. So first of all, remember, when we talk these problems, distances are the good old D equals RT. Distance, rate, and time. Not in the coordinate plane stuff. You should be able to know how to manipulate. If I got to solve for R, that's distance divided by time. Solve for T, that's distance divided by rate. You should know how to manipulate those things. What I want to do here, again, is I want to set up a chart so we can get things figured out. So let's look at the problem and see what we're doing here to begin with. Okay, got a kayaker. Let's say you did those rentals down on the river. Probably not when it's high water, but they're going to paddle 3 miles upstream. What should we all know about if you're paddling upstream? It's harder. And then 3 miles downstream. What should we all know about when in a river and when you paddle downstream? It should be easier. You're with the current. And did that in a total of 4 hours. So if you're going upstream against the current and then downstream in 4 hours, does that mean I'm only getting halfway? Now you're going upstream. It's going to take you longer to get to wherever this point is. And then downstream, not going to have to work as hard. You'll get there in less time in theory. It says he can travel at an average speed of 2 miles per hour. And that should read, oh, there it is, in still water. So if there was no current, this kayaker can go 2 miles an hour when they paddle. So what's going to happen when you go upstream? Obviously, your average is going to go down. What's going to happen when you go downstream? Well, you got the current working with you, so you're going to be able to go faster. The question is, what's the speed of the river's current? We know he can do this in still water. We know he traveled 3 miles, and we know it took 4 hours. So let's set something up to get organized. What did we do here in this problem? We went upstream, and we went downstream. So let's do that. We go up, and we go downstream. We have a distance. Again, use our formula here. Distance, so I'll label distance right here. We have a rate, and we have a time. Distance, rate, and time. So as we look at this, how far did we go? Well, it says we went 3 miles upstream. And we went 3 miles downstream. So what's this tell us? Our distances are equal. Key ingredient. Key ingredient. So now, what's our rate? Well, he can go 2 miles an hour. But if he's going upstream, what's that doing? Well, that's slowing you down. So if I can go 2 miles an hour, but I'm going against the current, that's going to knock me down in speed. All right? When we come down the river, what's that going to do to my 2 miles an hour? It's going to increase it. So whatever that current is, we go plus the current. Now, let's look at our time. Well, it was a total of 4 hours, but that's both those combined together, isn't it? Can I figure out the time based off of this? And yes, we can when we solve for t. That's our distance divided by our rate. Well, we have a distance, and we have a rate. So our time will be distance divided by whatever that happens to be. All right, we'll figure that out. Because again, it did take us a total of 4 hours to get upstream. So what part of that? And it's not just, I went 2 hours this way, 2 hours that way. No, the current slows you down. And then the current speeds you up. So let's figure this out. So if I'm going downstream, how's the time going to be figured out? Well, distance divided by rate. So now we look at the problem. Some people are going to say, well, the distance was the same. I'm going to set those things equal to each other. Well, we're forgetting one key ingredient here. We had a total of 4 hours on the river. total of 4 hours on the river. So don't jump to this conclusion that these are going to be equal to each other. Because if you think about it, if you're paddling upstream, it's going to take you more time to get to a spot than it does to get back. What we have is this. Our time going up the river and down the river was this for the rental or whatever you had. So 4 hours. So our total time will equal how long it took us to go upriver plus how long it took us to go down the river. So what's our total time? 4 hours. Up the river took us 3/2 minus the current. Going down the river took us, or we went 3 miles, over 2 plus our current. So again, we get some LCM action going on here. What's it going to be? 2 minus C, 2 plus C. So, the 2 minus C and 2 plus C gets multiplied by everything. I'm not writing them all out like I did in some of the other ones. So what happens here? Nothing cancels. But you have a sum times a difference. 4 minus C squared. All has to be distributed to that. So it's going to give us 16 minus 4C squared. Equals, now, as we look at it, the 2 minus C's cancel out. Gives me a 2 plus C times 3. So 6 plus 3C. Due to this one, the 2 plus C's cancel each other out. Leaves us with 6 minus 3C. So let's doctor some things up here and get to work. Cancels out. So we're going to have 12 over here. 16 minus 4C squared on this side. So a couple options you have. I'm going to subtract 16 from both sides. Negative 4C squared equals negative 4. Then what are we going to do? Well, we're going to divide both sides by negative 4. C squared equals 1. So we're solving the problem. We're putting the radical in the problem. Algebraically speaking, C will equal 1 or it will equal negative 1. What are we talking about though? Current of a river. Extraneous solution. So what did we figure out? That the current of the river is 1 mile per hour. The river had a current of 1 mile per hour. Like I said, I'm going to put more examples out there, so as I say the assignment, which some of you have already worked on, take your time, ask questions, and check out the future examples.